Okay, today's discussion is on the theoretical aspects of image processing, encryptions, uh, editing, what you want to do with it. Okay, so basically, I have a picture here of myself, and it was produced by an AI via an app called Voila. Okay, so I'm gonna use this to let you see that you could compress this, make it blurry, edit this, add color to this, add filter to this, and all that is under the name that the mathematical process called applying the operator onto your image. So your image happened to be the a function, and in this case, it's a function of two variables, x and y. Okay, so I could just write the image is equal to f with the r vector over it. So r is going to be x multiplied by x unit vector plus y times y unit vector. Okay, so basically the r vector will point from an origin to any specified point on the image. Okay, okay. So I'm gonna start with the okay. So let x the point on the image here be x1 to xn, which is an element of Rn. Rn here stands for in Euclidean space. So all the property of Euclidean axiom is applied. And then the other point is I'm gonna let it be t. Oh, I should let this equal to r as that, and then t will just be another variables, time variables. Okay. So rt is just a point in Rn, and then another parameters, complex parameter alpha. This alpha 1 all the way up to alpha n. It's an element of the complex space n. And then I have this generalized gamma functions. Gamma alpha is equal to gamma of alpha 1 times gamma alpha 2 all the way up to gamma alpha n. Then, of course, I have the differential operators. Partial x is defined to be the products of all the partial x1 to partial xn. Okay. And then here the interval a b here can be can be decomposed down to a1 comma b1 Cartesian products with a2 comma b2 and all the way up to an bn. Okay, again a and b are points in Rn, so it has n factor. All right, so let us define the first operators. In this case, the partial Riemann-Liouville fractional integrals of order alpha k be defined as follow. Okay, so you see ak here. So this here is the operators acting on the function, or in this case, the image is defined to be 1 over the gamma function of alpha k. The integral from ak to xk, um, and then the kernels xk minus tk with the alpha k minus 1. So the kernel here, you can think of it as like a memory function. Uh, it it tells you information how you get from state A to state B and so on and so forth. And then of course the function is in here, but you only pick out the tk components. So the end result is that you x1 to xk minus 1 and then tk, and then you have xk plus 1 all the way up to xn dtk. Here x are all greater than a. Okay. And you need to have this condition too, that the real part of the alpha k must be equal greater than 0 to ensure the convergence of the above integral. Okay. All right. So the
I got to minus and like plus.
yeah.
Okay.
So the right-handed partial derivative is defined similarly. D to the alpha k, instead of a to x, you have a ax xk to bk. Okay, so x is going to be smaller than b's. So it's defined the same way: 1 over gamma of alpha k, except for the kernel of here is reverse itself. So you write the tk to the left and then the xk, and then the power would be the same, alpha k minus 1, and then f of tk dtk. All right, so the next step is to get the full fractional derivative of order alpha, and it's defined this way. So d to the alpha with a plus sign at the bottom on the functions is just an info of these operators acting on the function. Okay, so you have a1 to x1 raised to the alpha, a2 to x2 raised to the alpha, and so on and so forth. And it's defined to be 1 over gamma of alpha. Remember, gamma function is equal to alpha 1 times gamma alpha 2, and all the way up to gamma alpha n. Okay, and sometimes they call this this formula here the Cauchy integral formula. Okay, and everything will be the same. Notice here the dt to the n is the volume form. It's like a dv in 3 space. So it's being multiplied by dt1 all the way up to dtn. Okay. And then the next object we need is the right-handed. So d to the alpha with the minus sign right there acting on this function. And it's gonna be 1 over gamma alpha. Remember, this is a multi-dimensional gamma function. It runs from 1 to n. Okay. Except the limit integration is reverse here, so you're going from x1 to b1 and all the way to xn to bn. Then of course the kernel itself is also reversed. You write t first and then the x. Of course, with the full power, alpha minus 1, and then of course f of t dt k. Okay. All right. So this is equivalent to they call it the left-handed. Okay, because the argument x is less than the parameters b. Okay, so in order for us to do any computation with a two-dimensional image, we need to construct a special operator. It's called the Riesz fractional derivative. But first, we need to know some elementary result from the theory of Fourier transform. Okay, because that would be crucial for understanding that result that we're going to construct here. Okay, so in n dimensions, this is n dimensions, so this is an Rn. Okay, so this is in Euclidean space with all the Euclidean axiom. Okay, so you see here the f script f, and then I have a bracket, and then this is the original function f of r. Remember, f of r is my image, two-dimensional image, and it's defined to be the integral over Rn. It's no longer from minus infinity to just positive infinity in the case of one dimensions, but now there's going to be n many of these in the integral. And so you have this f of r. So this is the image right here. And it's being transformed by this kernel, e to the I r hat. This r hat here is a vector. And then this here is you can think of this as a wave number. or a frequency number, and it's also a vector. When you dot the two vector, you get a scalar quantities. Okay. And then since we are integrating over the whole volume, this dr here is raised to the n. This is called the volume form in n dimension. In n dimension. But for two-dimensional image processing, we just use R to be the x and y, just two variables. Okay, so you see this here will tell you that when you multiply this the image with this kernel, and then you integrate this over all space, you get this f with a hat, and then this new variable here. So the new variable here is called the frequency variables. Okay, and the hat just tells you that it's already been transformed from the time domain representation to the frequency domain representation. Okay, and then of course, if you want to inverse Fourier what you just transform, so you plug this into this operator here. Now the inverse Fourier should cancel the forward Fourier transform, and to see that, the inverse Fourier transform is defined this way. It's 1 over 2 pi raised to the n power, and then I have a volume integral of over Rn. So this is no longer just minus infinity to infinity. It's just you have n many of these minus infinity to infinity. Okay, and then this f hat here is the Fourier transform of the image. So now I plug that into here, multiplied by the new kernels, e to the minus I r dot c hat dc. Okay, so what I do next is I'm gonna put this object, the Fourier transform, into here. Okay, but this is equal to this integral. So then I have two. How about this? I have a r to the r. I have one integral involving Rn, and then I have another integral involving Rn. So together there are r raised to 2n power. Okay. So all this here is just a dummy variable. So I'm just going to rewrite f hat of sigma c is equal to f of r prime. So you see there's a prime there. And then divided by 2 pi to the n power. And then I'm combine the two kernels together and write it like this. And then I also switch my volume form. So I have a dc to the n in here. It turns out that the integration of this kernel like this over 2 pi n dcn turn out to be a n-dimensional direct delta functions, which is this thing right here. Okay. And so this result reduces to, so now I did the one integral already, so I left with the other one. So I have the functions as a function of r prime and the delta function. So whenever you see r prime, you just replace this by r. That's what you do with the delta function. So I integrate this, and so I left with the function. So wherever I see r prime, I replace that by r. Okay. So f of r is the original picture, this picture. Okay. So Fourier transform is a specific integral equation. and fractional derivative are just ordinary derivative on fractional integrals. That's how you should remember that. Okay. So next time we're going to do many examples involving fractional Fourier transform or just fractional integrals, and see what can we do differently. Can one compensate the other? You know. So, and then I will also show you more computer stuff too. Okay. So see you guys next time.